Hello and welcome to the presentation of the paper on certifiably adversarially robust detection of out-of-distribution data that I did together with Meinke and Matthias Hein at Uni Tübingen. When we have a deep neural network classifier for CIFAR-10 that is trained for distinguishing dogs and 9 other classes like cats and sheps, and we now feed an input into this classifier that does not belong to any of these classes, like the chimpanzee here on the right, then the model is often still very confident that it classifies this input correctly. Like here, it is 100% certain that the chimpanzee is a dog. We call such inputs out of distribution, short OOD, and by confidence, we mean the highest predicted probability in any of the classes. One problem with such high confidence predictions is that the model does not recognize that it operates outside of its specification and should trigger human intervention, or, for example, if it's a self-driving vehicle, it should better slow down. Now there are approaches like outlier exposure that produce models that do have low confidence on OOD inputs, but for those models it can still be possible to construct imperceptible perturbations to arrive at images like the slightly manipulated chimpanzee here on the very right, where even outlier exposure has 100% confidence. What we now aim to do is to guarantee that no such high confidence perturbation exists, and for this we regard the context of an L-infinity threat model, which means that each individual pixel value can be changed by up to a certain epsilon to maximize confidence, and then we look at the worst confidence that can occur this way. Using interval-bound propagation, we derive mathematical upper bounds on the confidence, and then, during training, we minimize those upper bounds on OOD inputs, and at the same time, we keep the cross-entropy loss on the in-distribution. What we get from this procedure are good models that indeed provide low confidence guarantees on many kinds of OOD inputs, and those guarantees even generalize to new distributions that have never been seen during training. While other provable robustness methods severely worsen test error, with good, there is almost no drop in in-distribution accuracy. Finally, regarding the quality of the guarantees are often better than worst-case samples we can find for standard methods. For example, we can guarantee that no small perturbation increases the confidence of good on this chimpanzee above 22.7%.